Push a baseball bat at its middle and it slides across the table without turning. Push the handle with the same force and it spins away wildly. Two completely different motions from one identical push. Yet hidden inside both is a single point that accelerates in exactly the same way. Find that point and the whole system of particles starts obeying Newton's second law as if it were one. We already have the center of mass, R sub cm, the mass-weighted average of position, differentiated once with respect to time, and every position vector becomes a velocity. The velocity of the center of mass, V sub cm, equals 1 over the system mass times the sum over all m particles of m sub I v sub I. Look hard at that sum. It is exactly the momentum of the system, the vector sum of the individual momenta. So V sub cm equals P sub cis divided by m sub cis. Turn that around and you get something remarkably compact. The momentum of the entire system equals its total mass times the velocity of its center of mass. Now feed that into the law we proved for a system. The external force equals the rate of change of the system's momentum. Substitute m sub cis v sub cm for the momentum. The individual masses stay constant, so the total mass comes straight out through the derivative, leaving the total mass times the derivative of v sub cm with respect to time. That derivative is the acceleration of the center of mass, written a sub cm. So the external force equals m sub cis times a sub cm. Set that beside the law for a single particle. Force equals mass times acceleration. The form is identical. An entire system of particles obeys Newton's second law at one point. Read what that result licenses and what it does not. It does not say the internal forces disappeared. They are still there, particles pushing and pulling on each other. It says they cannot accelerate the center of mass because they cancel in third-law pairs and never survive into the sum. Only what reaches in from outside counts. And notice what is missing from the equation. Any mention of where the external forces are applied. For the linear motion of the center of mass, you may slide every external force onto that single point, add them as vectors, and treat the whole system as one particle carrying all the mass. Here is the payoff, and it is the question the chapter asks. A baseball bat lies on a nearly frictionless table, seen from above. Mark 3 positions along it, position 1 at the handle end, position 2 at the center of mass, marked with a cross, and position 3 at the barrel end. You push with the same force F perpendicular to the bat at one of those positions at a time. Will the acceleration of the center of mass be greater than, equal to, or less than the acceleration you get by pushing at either end? Work from the law we just wrote. The acceleration of the center of mass is the external force divided by the system mass. Only two things appear in that expression: the force you apply and the mass of the bat. Neither one changes when you slide your hand along the bat. So the acceleration of the center of mass is equal in all three cases. The point marked with the cross picks up speed at exactly the same rate, whether you push the handle, the middle, or the barrel. That is not the same as saying the motion is the same. Push at the center of mass, and every particle in the bat has the same acceleration as the center of mass. The bat translates, it slides across the table without turning, and every line drawn on it stays parallel to itself. Push at one end and the particles no longer move alike. The center of mass still accelerates in the direction of your push at the very same rate as before, but now the particles also circle around it. The bat translates and rotates at the same time. Same center of mass acceleration, completely different motion. The equation was never a promise about the particles, it is a promise about one point. Now push the idea to its limit. Set the external force to 0. Isolate the system completely from its surroundings, so nothing reaches across the boundary. A system with 0 external force is what we call an isolated system. And look what follows. the rate of change of the system's momentum is zero. So over any interval, the change in the system's momentum is zero. The momentum of an isolated system is constant in magnitude and in direction. The center of mass equation says the same thing in a second language. If the external force is zero, then m sub cis times a sub cm is zero, and the mass is not zero, so the acceleration of the center of mass is zero. The center of mass of an isolated system drifts forever in a straight line at constant speed. Constant momentum is a claim you can cash out particle by particle. Before the interaction, the momentum of the system is the vector sum of the individual momenta, m1 times the initial velocity of particle 1 plus m2 times the initial velocity of particle 2, and so on through the system. Afterwards, it is the same sum rebuilt from the final velocities. The momentum is unchanged, so those two totals are equal. Hold on to the word vector. These are not sums of speeds, they are sums of vectors added head to tail, direction, and all. Two particles flying apart in opposite directions can carry a total momentum of exactly zero. And watch the subscripts here. In these two expressions, I means initial and F means final. They are not particle labels. Real systems are rarely isolated, so take the other case. The external force is not zero. Every external force on your system is one half of a third law pair. Its partner acts on the surroundings, meaning everything outside your boundary. So the total force on the surroundings is equal in magnitude and opposite in direction to the external force on the system. And all the internal forces within the surroundings cancel among themselves, exactly as they did inside the system. Add the two forces and you get zero. Now apply the same law twice. The external force is the rate of change of the system's momentum. The force on the surroundings is the rate of change of the surroundings' momentum. Their sum is zero, so the change in the system's momentum plus the change in the surroundings' momentum is zero. That is the principle of conservation of momentum. One chain, four links. The momentum of a system is its total mass times the velocity of its center of mass. Differentiate, and the external force equals the total mass times the acceleration of the center of mass. Newton's second law for a crowd of particles, holding at a single point, no matter where you push. Switch the external force off and that point coasts because the momentum of an isolated system never changes. Leave the force on, and the momentum does not vanish. It moves next door. Whatever the system loses, the surroundings gain. Momentum is never created and never destroyed. It only changes address. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.